Hey friends, we've reached the end of chapter 6, which is pretty cool. We're on indirect measurement, which gives us the power, using all the tools that we learned early in the chapter, to actually measure things that we can't measure straightforwardly. So in this case, we have a flagpole, and this flagpole is casting a shadow, and that shadow is 15 feet long. And then we have the known height of a person, which is 6 feet, and their shadow at the same time of day is casting, their shadow is 4.5 feet. And what we can do is use the similar triangles that are created, because yes, there are similar triangles that are created here, to actually find the height x, and that's what we're going to be working on today. And I think you guys from your work with similar triangles can actually do this calculation, but we'll save this for later, or perhaps I'll let you guys do it on your own. Let's take a look at our vocabulary. So our vocabulary today is indirect measurement. We're using properties of similar triangles to measure things difficult to measure, like that flagpole in that example earlier. Let's see if we have any practical examples we can use. So here we have, this is called using shadow reckoning. So we're using the shadow, and this is very similar to the picture we had above. Find the height of the lamppost if the friend is 5 feet tall with a shadow length of 52 inches, and the lamppost casts a shadow that is 108 inches. So whenever I have a situation like this, I do like to write down the information that I have. So I'm going to put 108 inches here, because that's the length of that shadow, 52 inches here. And what's the other given information that we have? We've got that the person is 5 feet tall. So our friend is 5 feet tall. Our friend. Okay, so the thing that I'm realizing right now is the inconsistency of the measurements. I've got feet here, inches here, and this looks like meters, but it was inches originally. So what I'm thinking I would like to do, I think it's pretty easy for me to change feet to inches. So I think I'm going to rewrite this and put it in terms of inches. So instead of having 5 feet, I know that if I go from feet to inches, basically I know that there are 12 inches in 1 foot. I know you guys are like, do we have to do this again? Yes. And I multiply it together and I'm left with 60 inches. So instead of writing that as 5 feet, I'm going to write it as 60 inches. So with that now taken care of and in mind, let me see, put it in there. So we've got 60 inches. Now I feel like we need the same units. Now I feel like we can nicely set up a situation where we are where we're going to make a proportion. And so our proportion is x is to 6 as 108 is to 52. We could have done it the other way. We could have done 6 is to x as 52 is to 108, but notice we're going from corresponding sides of the triangle that's created by this situation. So now we just need to solve. Okay, before we get into calculating, this should be 60, and this is x is to 60 as 108 is to 52. Sorry about that. I know you guys are like, oh, crazy lady. All right, so we're going to do 108 times 60, and that's going to be equal to 52x, which gives us 6,480 is equal to 52x. Like usual, we're going to divide both sides by 52. And when we do that, we're going to get that x is equal to approximately 124 and 0.6. And so this would be inches. Inches, we could use that. That's fine. But I think, let's see if we can figure out what it would be in feet. To translate our inches to feet, we're going to end up dividing by 12, and when we do that, we see that the lamppost is approximately, so this would be inches, let me put that there, is approximately 10.38 feet. So, 10 and a third feet or something like that. All right, so that's how we would do it. So a lot like what we're used to, a little bit of changes in the units we had to handle, and simply dealing with similar triangles, stuff that we know how to handle. All right, let's look at example 2, find the missing measures. And in example 2, we have two similar triangles, but this one is a little bit not noticeably oriented, right? It's kind of oriented in a way that we're not used to. So we need to be really careful, but we've dealt with this before. Remember the key? The key was to look at the lettering and to make sure we know what sides correspond with what. So I'm going to go through and I'm going to do what we did last time. So here's my X, and x is to b. So here's my x and here's my b. I'm going to put them in the same color. And then the next one will be y. Here's my y, and y is to a, right? They're in the same position. And then C is at C, so I don't really have to do anything about it, but just to be fun, I'll just color the C green. It is to itself. So what does that mean? How does that tell us what we can do? Well, what we're looking for is to find the distance across the river, and here's the river. This is the river, and the distance, let's mark it in X. Now that we've marked that in X, now maybe X is confusing, right? Because we're using X as a side. Let's mark that change, y'all. Let's mark that as D. Let's change that. Let's mark it as D. Because D is just a fabulous, fabulous letter. Okay, so we'll mark it as D. And that's what we need to find, distance. That works. All right, so if we need to find that distance, we need to kind of orient ourselves. We've got to use what we've got. We've got that. And we've got that to get what we want. We want this. So we have this matching pair of sides, right? Because CX and CB are corresponding sides. So small triangle, 5.2. I don't know if you guys can see that. That's what that measure is, 5.2 meters to 14.7 meters. So 5.2 to 14.7 is equal to, now I've got to do red blue to red blue, which is, these are corresponding sides. So 3.8 to D. And here is like one of the situations why I keep asking you guys, even though it seems like really easy to sometimes solve these. The reason why I ask you guys to do the cross multiplication, because when you have a situation like this with decimals, it's just not convenient. So what we're going to end up doing is multiplying 3.8 times, I use the old-fashioned times sign, 14.7, and that's equal to 5.2 D. So we'll multiply this, divide by 55, and we get that 55.86 is equal to 5.2 times D. And when we divide both sides by 5.2 to isolate the D, we get 10.74 meters is the distance, or the D value, across the river. And that really is it. I mean, it's really applying what we've learned to real life situations, and that's what you're going to see in the text with your problems. Here's your assignment. Your assignment is as follows. Indirect measurement, pardon me. We've got a few problems, not a lot, but you realize that these problems you're going to have to set some stuff up. So make sure you give it your best, your try, and we'll talk during class. I look forward to talking to you guys soon. Bye-bye.